Oh, for God's sake. It's wide, prof. Ugh. Good afternoon, everyone. By which I mean good evening. Kind of funny. Let me just fix this thing, and hopefully That's less wide prof. This is normal prof of normal width, I think. There we go. All right, there we go. Excellent. All right. First thin prof, now wide prof. What's next? Let's see. Let's see what's next. Can I do green prof? Oh, it's not. It's not cooperating. Eh. Whatever. Okay. So, I have received a question. Is it possible to see your, what you got wrong on the test? I think it should be. If anybody knows of a way to access, like, view your attempt, if anybody knows the way through the interface to that, it would be a useful thing to put in here. Into the lecture. Quizzes. Let's see here. Set up reports. There are no reports available. Add report. Report type, question statistics, score distribution. What? Question details. This is... that's not what I'm looking for at all. Klein bottle. You can't? Like at all? That seems dumb. Pardon me. Published to LOR? What's LOR? Learning Objectives Report. Blah. Like, you can't go in and see? That seems like... eh. Properties, maybe? Submission views, that looks like a tab. The following is the submission view that will be released to the users. Oh! Default view? Show questions, yes. Show all questions with user responses. Yes. Yeah, because there are lots of questions. Show question answers. Show question score and score out of. Yes, good, good. Show out. We don't use outcomes. Show class average. Sure, why not? Show score distribution. Sure, why not? Okay. Save! Saved successfully. Save and close. Bing, bang, boom. Can you try it now? By pressing submissions and then attempt one, but you would have to enable it on my side. Forbidden knowledge. Yes. So, can someone please confirm? Yeah, awesome. Excellent, excellent, excellent. Yeah. I mean, yeah, what's the point of doing the quiz if you don't get any feedback on the quiz, you know? Like, holy smoke. All right, excellent. Glad we got that sorted out. Did I call you guys fancy meat computers yet? I don't think I did. Good evening, fancy meat computers. So, there we go. Excellent. So, I suppose I should, like, talk about the quiz a little bit. So, I actually released it so that you guys can view the statistics, but I'm just going to pop them up on the screen right now. So, the distribution for the quiz was actually kind of like, I want to say surprisingly low. Like, I expected an average on this in like the 80% range, and we got it in the high 60s. The correct answer is not displayed for written response type questions. Yeah, that's because I never gave a correct answer for the written response type questions. There is no correct answer. If I remember correctly, pretty much everyone got, you know, well, everybody got at least half the marks for those questions. I'm dumb and I clicked the wrong answer for something. Well, nothing I can do about that, I'm afraid. What you submitted is what you submitted. But yeah, so the marks were a little on the lower side compared to what I was expecting. So, I hope that isn't a portent of things to come. But, yeah, it sort of ended up with like a reasonably standard-looking normal distribution, which is kind of cool. Except for the fact that, like, you know, 20 users all piled up at, like, getting, you know, 80% or so. Which probably corresponds to 5 out of 6. So, yeah. So if I have a question about one of the ones I got wrong, do you just post it on Piazza or something? Yep. Yeah, you can post it to Piazza. Yeah, absolutely. It doesn't matter if you knew the right answer. It matters if you wrote the right answer. You're also being graded on your ability to transmit the information from your brain to the paper. You are implicitly being graded on that every time you're being ungraded on anything. Instructions are executed by the ALU, however, they are performed on the registers. Well, the ALU loads data from the registers into the ALU, and then it executes them there. What does using a high-level language... what effect does using a high-level language have on the non-recurring engineering cost? Well, using a high-level language means that it's easier to program, right? Because it's easier to program in that language, it doesn't cost as much to develop the program. So it reduces the cost, the non-recurring engineering cost. Yeah, I know you're just memeing. Wait, so are you telling me that instruction results are not stored at the grocery store? Yeah, that's correct. There were a couple of meme answers in there. So, might as well get to the lecture content then. When you guys are filling out your course evaluations, please fill out that all of the assessments are graded in a reasonable time frame, please, because I got the quiz results back to you the next day. Please give me a good result. Please give me a good evaluation. So last time we were talking about a couple of different things. We talked about push-pull versus open drain, and we talked about slew rate, and we talked about the Schmidt trigger. Local variables aren't stored in happy memories now. Midterm marks same day, then we'll talk. Well, like, if the midterm is going to be on paper, then I at least have to, like, physically carry the Scantron sheets to a Scantron machine, so, you know. We'll see how it goes. Man, entitled Zoomers, eh? If your electricity comes from fossil fuels, your PC is kinda dinosaur powered. There you go. Could I release the rest of the quiz questions? Oh yeah, that's not a bad idea actually. Yeah, let me I won't do that now because I'm kinda, you know, in the middle of other. Where's my bloody notebook? Oh, there it is. It's under my other two notebooks. Yeah, actually, I don't think that's a bad idea, actually. So, yeah. Release all questions. Good. That's okay, Ethan. I have this thing right now where, like, I'm being so, like, my sarcasm is at such a level that people can't tell I'm being sarcastic. Yeah, it would be good review. I was also kind of thinking, like, maybe there's a way for me to be able to set it up so that you can take the quiz multiple times, but only the first one that was, like, the actual one is the one that gets the grade. I think I might be able to set that up, too. So, but yeah. Anyway. So, Schmidt triggers. We talked about Schmidt triggers. So let's kind of, let's zoom right in on the actual circuitry that's used for one of these general-purpose I/O ports. So, this is the basic structure of an I/O port with the I/O pin over here, and you can see it's yellow because it's a gold pin, right? You've got protection diodes on either side. The pull-up and the pull-down resistors here, that's what's configured when you're in pull-up, pull-down mode when you're reading input. You can see that the push-pull output control is right over here. The Schmidt trigger is right here. You have an analog. You can read analog, and that just reads straight off the pin with no interfering electronics, because you wouldn't want any. You've got an alternate function input immediately after the Schmidt trigger. You read the read to data registers just comes directly off that read line. So the top half is the read part, and the bottom half is the write part. So yeah, what I don't see pictured here is the open drain. The open drain portion of this, but you can see that the input driver, the sub-circuit which is called the input driver, consists pretty much of the Schmidt trigger with a couple of connections, whereas the output driver actually contains the the push-pull circuitry and the open drain circuitry. So, incidentally, whenever you see one of these trapezoids, that's a multiplexer, right? So, you have a GPIO mode register. that is in memory. We'll get to the details of how the memory is mapped on these guys, but when you have so you've got 4 basic modes, right? You've got your input and output. You also have alternative function, which depends on the implementation, and you have analog. So mode is an important thing to select, of course. You can also select the output type. 0 gives you push-pull, and 1 gives you open-drain. So there's another register called O-type R, which allows you to select between open-drain and push-pull. PUPDR, or PUPDR, is the pull-up, pull-down register, and that configures whether or not the thing is configured in pull-up or pull-down mode. You can actually do neither pull-up nor pull-down, although that's not recommended. So, that's how your various configurations get configured. Any questions so far? We doing okay? I'm going to try to get through this a little bit. Like, I'm going to try to move here, because, like, hypothetically speaking, we have close to 30 slides to get through in the next, before the end of class. So let's talk about the memory map of the Cortex-M, which is the one that you guys will be using and are using. So, of course, you guys remember, hopefully from the last slide deck, that you have your instruction memory at the bottom. You then have your working SRAM memory, which is used for the stack and the heap, etc., etc. You then have peripheral memory, external RAM, external device, and system memory. So system memory is like your basic stuff that has to be there for, for operating system type purposes. What was AF again? AF, where was that? Where do you see AF? What slide was that on? Yes, thank you, Memer. Living up to your name. I can't see an AF. Alternate function. Oh, yes. Sorry, yeah, right here. Alternate function. Yeah. Thank you. So what we're concerned about, so the external RAM deals with off-chip memory for data. So if you have like an external SRAM chip or something, that would be mapped to your external RAM. External device would be something like an SD card, which may or may not be, actually plugged in. And the one that we're interested in today is the peripheral memory. So this peripheral memory section includes your general purpose I/O memory map region. Not sure what AHB and AH. Yeah. I'm not sure what those are either. Let's look it up. So AHB in microcontroller. Ah, interesting. So it's about the bus architecture. AHB. Yeah, okay. The first AMBA buses were the Advanced System Bus, the Advanced Peripheral Bus. In its second version, ARM added the High Performance Bus, AHB. Yeah. So it's a bus for communicating with various peripherals. That's cool. Yeah. Yesterday I got my course evaluations from last semester, And one of the things I was criticized for by one student was that I often say I don't know something when somebody asks a question. And, I get that, probably I should have more things stuffed into my brain, but, I like to think that it's better to, take the time to look up the correct information and give that to you instead of, making something up and being wrong. Is the organization of this memory just for microcontrollers, or is it the same setup for something like a stick of RAM for a computer just a bit smaller? So this memory mapping system will be, like, it's first of all, like, the addresses themselves, right? That's specific to the Cortex-M4, right? Other ARM architectures will have, like, the same layout, but with the, the exact boundaries of the different memory regions may be slightly different depending on which ARM controller you're using. Some of them might not have as much memory, so you have to compress it down more. Some of them have more memory, so you have to expand it, that sort of thing. But no, this is ARM architecture that we're talking about specifically right now. The whole memory mapped, memory mapping of I/O, I do not believe that's the sort of thing that goes on inside of your computer. But that's a good question. Thank you, David. So, inside of your peripheral memory, you have 1 kilobyte regions of memory which are dedicated to GPIO. They sort of... It's kind of interesting. There's a lot of, like, dead space in the address regions for these things. As we're going to see, all of the information that the GPIO pin requires does not occupy 1 kilobyte. Not even 1 kilobit. But they assign it 1 kilobyte, I guess, imagining future expansions. So, if we take one of these particular regions and we break it down, we get all of these registers, which we're referring to here, are contained at the following locations inside of your memory, inside of your GPIO memory region for whichever port you're on. In total, you've got 48 bytes of memory, which these various registers contain. And before you ask, I wouldn't quiz you on the, like, ODR is at register this, lock R is at at memory address that. I wouldn't quiz you on that sort of thing. But what some of these things are used for is totally fair game, particularly the ones that are on this slide. Just so you know. Because I'm a nice guy, I tell people these sorts of things. So, each of these registers has 4 bytes, so this is 32 bits in width, right? Let's say we want to set the pin A14 high. So that is the pin on GPIO port A, bit or pin 14. And remember, this will be 0 indexed. Right? So, this is an output operation. So, we need to talk to the output data register, ODR. So, of the ODR register, which again contains 4 bytes, in Little Endian, you have basically the big stuff is at the beginning and the little stuff is at the end, right? So the 0 byte is on the right and the 31 byte is on the left. But you can see that, like, each of these 8 bits sort of slots into one of these rectangles. Boink, etc., etc. Boink. Boink. So, given that the port is composed of 32 pins, if we want to access pin 14, we'll know which of these bytes we want to set the bit in. Remember that this is memory mapped I/O. In order to drive a 1 to that pin, all we have to do is set the correct corresponding bit in memory. Right? The trick, of course, is that everything is addressed in, you can only access, 32 bits at a time, right? So here's your operation. We take the memory address of ODR, right? We cast it as a pointer to an unsigned integer of size 32, and we then dereference it, right? Dereferencing as in the pointer operation. We then perform bitwise OR with the value 1 left shifted by 14. So that puts the 1 in the correct spot. Regardless as to whether this was a 1 or a 0 before, the OR operation will set it to a 1. So here's a question for the class. This is 1UL. Does anybody remember what this means in C? Like, what is 1UL? What the heck does that mean? Can anybody tell me? Unsigned long int. Yes, thank you. Thank you, Tom. Yeah, so this is 1. So the way that you take a literal and you cast it as being one data type or another is you suffix that literal with some characters. U makes it unsigned, L makes it long. So there you go. So I guess that would seem to imply that in ARM architecture, int by default is 16 bits and long would be 32 bits. That would be interesting if it were true. Microinductor? No. Let me see. ARM C programming int size. Oh, it's 32 bits. Strange. So, while I don't necessarily understand why they would need to cast it as a long int when a regular int is already 32 bits in ARM architecture, the unsigned bit is kind of important. Well, the unsigned characteristic. When you represent negative numbers, like remember way back when you took 2MP3 with me, for those of you who did, and if not, remember your C programming. Think back to the manner in which negative numbers are represented, right? Negative numbers are represented in 2's complement. So -1 is all bits set to 1. So basically, if you perform this left shift operation on a integer that's not unsigned, if you push this 1 bit all the way to the end, you'll actually flip the thing negative. But yeah. How is an unsigned long int contained in a single bit 14? It isn't. That's no, it just takes 1, so this operation just creates a 1 with the correct number of zeros in front. Isn't it because int used to represent short int or something like that? No. No, it's, no. I did cover this. I covered it pretty in-depth, actually, the difference between short int and long int, and int, just int. So, no, what it does is it just, like, in binary, it just puts the correct number of zeros. This isn't exactly the correct number of zeros, but it just puts the correct number of zeros in front of it. That's, like, 1 UL is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 23, 24, 25, 26, 27, 28, 29, 30, 31. There we go. That's all the bits, right? So 1 UL left shifted by 14 is equal to this guy, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There you go. So that's what this, like, that's what left shifting it by 14 does, right? So then you take the register and you perform bitwise OR with it, and whatever the state of that register is, the 14th bit will be flipped to 1, or remain 1 if it was already. So all of this for one input-output pin or multiple. All of this is for one input pin. Of course, if you wanted to set many at the same time, you could totally do that in one operation. You know, if you wanted to set, 14, 12, and 8, you could just do it that way. And then all these get set in one operation, which is kind of cool. And fast. But yeah, all this to set one output pin, correct. Although, from a C programming perspective, this is actually, like, very, very little work to perform something as complicated as GPIO. Because of the memory mapping system. So, you can introduce a structure which will label all of the different registers for you in a very convenient manner. GPIO typedef. So if you define GPIOA as a, this memory address cast as a structure, then you can actually access all of these registers directly using structure syntax, which is pretty cool. So that address is just the address of the value that we're performing bitwise on. Yes, that's correct. This is just the address that you're performing the operation on. Correct. You can actually, you can map, you can redefine this operation right here using a definition in C, and that gives you some very useful results, like being able to address things just using names, which is much, much more convenient than having to pass around the actual addresses all the time. And it also modularizes it so that if you're, if you have to port your program to some other ARM architecture that uses a different address for the GPIOA port, then all you have to do is, go into your definitions file and modify it, which is probably already done for you. So if we want to change bit 15 instead, we would change the 14 to a 15. Yes, correct. Correctamungo. So let's shift gears a little bit. Talk about the LEDs that are on the board, or on a board. This is a different board than the board we have, but this portion should be the same. So we've got the LED R and LED G connected to pins PB2 and PF8, so B2 and F8. This might be different on slightly different on the board that we have, and so if you write high to to pin B2, the LED turns on. Low, it turns off. Very straightforward. On slide 26, all of those sections like AS, CR, BRR, etc. are shared by all of the I/O pins, and each section, every pin has its own register. So 26. Okay. So going back to our view of the way that the peripheral memory is mapped, right? You have each of these GPIO regions. These regions contain all of these individual registers, or, you can think of them as registers, but they're probably not stored as flip-flops. Or they might be, who knows. But, yeah. All of these different registers exist inside of the GPIO port A region. With this guy, it's the same ones, it's the same registers. All we're doing, right, is so this is kind of the way that structures work, right? With a structure, it lines up all of the fields in sequential memory, right? So mode R is the first one. O-type R is the second one. By declaring them with the specific width of each of these registers, basically it's declaring names for each of these adjacent memory regions, right? So all of these mappings are for a single port, right? But for example, so the output data register, right? Like we've talked about setting the pin high or low using the output data register. If you wanted to set an option for one of these things, like for example, output type, right? If you wanted to set output type, that's O-type R. O-type R would have, it also has 32 bits. So setting bit 14 of O-type R configures whether or not pin 14 is in push-pull or open-drain configuration. Hopefully that sort of is what you're getting at there. What would happen if we changed it to one of the other four addresses but kept the UL? Well, see, if you did that, then you would be offsetting the bit that you're writing by, however many bits you offset it by. Like if you take this address instead, then, rather than bit 14 ending up in this region, bit 14 would end up in this region. You'd offset the whole thing, right? Good. These two pins on the STM are GPIO pins. Yeah, one's attached to port B2 and the other is attached to port E8. Yes. So, we're actually going to talk about AHB2. So, AHB2 Peripheral Clock Enable Register, right? Does every single one of these registers have 32 bits mapped to each pin, or is there a generic register that applies to all pins as well? Now that I'm thinking about it, I think that's probably, I think there's... So, I think there's 16 pins, actually, rather than 32. Give me a second to look it up. Let's take a look at the data sheet, shall we? So, IO, GPIO-A. Oh, come on. Is this like one of those short ones that's just really a... Yeah, this doesn't actually have any useful information on it. At any rate, the reason I'm making that observation is that if we take a look at some of the options here, some of these things require 2 bits. So that would seem to imply to me that we have 16 bits that we're dealing with here, not 32. And that something like, for example, mode R maps 2 bits to every one pin rather than 1, so it composes 32 bits instead of 16. So I'm a bit confused what you meant by the registers got offset if you started at a different address. Well, like, it's the same write operation regardless of what the starting address is, right? So, like, there's really no difference between starting at, you know, address 14 or address 18. 18 will pop you into the next register, but, you know, if you write at 16, then, you know, it's the same operation, just on 4 different bytes, right? Generally speaking, though, you should just never not write along word boundaries. Always stick to the word boundaries. Can you explain what define GPIO-A is doing exactly? Yeah, I can do that. So, define GPIO-A right here. Right? We take the memory address of the GPIO-A port, right? We cast that as a structure, this structure here, right? We cast it as a structure. And then the define, like defining that as a macro, means anywhere in the code that we use GPIO-A, it will substitute this piece of code, right? So this guy gets copied in anywhere we have something like this or something like that, you know, actually right there. So, like, that's how a define statement works, right? So the reason this works is this is how structures work in C, right? Think about arrays, right? Structures are kind of like arrays, except the size of whatever the element, like the elements are lined up, and however much size they occupy, that gets mapped onto the memory, right? So the first 32 bits get assigned to mode R. The next 32 bits, O type R. The next 32 bits, O speed R. And that just means that all of these register labels are just plunked in at the memory addresses that are correct, right? Or at the memory addresses that correspond here, right? Like you could totally, if you pulled up a C program and like set this up and printed the address of each one of these fields of the structure, once you've set it up with this define statement, you would get each one of these addresses, right? So really this is just a fancy way of taking all of these memory addresses, mapping them to the actual names of the registers so that we can deal with the names instead of all of these memory addresses all the time. So, so there you go. So GPIO-A corresponds to the section of 32 pins, and then GPIO-A is an ODR so, let me see here. GPIO-A corresponds to a section of 32 pins, 16 pins, I think. Although I'll have to look that up, because that's really the sort of thing I should know. And then in GPIO-A, there is an ODR section with 32 bits, where each bit corresponds to one of the 32 pins. Yes. Yes, that's correct, Connor. David, so the reason it is 4 bytes is because it's 32 bits, and a long int is 32 bits. Yes. Yeah, actually, I looked that up. In ARM architecture, long is 32 bits. Are all of these memory addresses the same name, like that address across each device? So, Ryan, yes. So long as it's the same chip, right? So these memory boundaries are true for the Cortex M4. If you're dealing with like the Cortex M6, these might be slightly different, right? These memory addresses, well, they might be more than slightly different. These memory addresses will vary by the processor, right? Which is why these type of things tend to be put into defined statements, which travel with the processor so that you can just refer to the individual addresses. What does volatile do? Let's see. Volatile, where is that? Oh, volatile. You know, I don't know. Let me take a look. C programming volatile keyword. So, as near as I can figure out, so I found this source. Oh, and they want me to sign up for something. Get out of here, you. So, it is used to inform the compiler that the variable value can be changed at any time without any task given by the source code. So it's like, so volatile is, it is used to prevent optimization on objects in the source code. Oh, all right. So using the volatile keyword will prevent the compiler optimizations from messing with it. Because so if the compiler optimizations like decided to come in here and like move this stuff around because it would be slightly more optimal, you would lose the mapping between the memory addresses, right? So you don't want the compiler touching this, so you label it volatile. That's what that does. So I get what GPIO is, but what does the A at the end? So that just means port A, right? So your microcontroller will probably have several GPIO ports. Port A, port B, port C, port D. You have a lot of pins available. They group them into ports. So this is what we've been talking about, port A, just because we have to talk about a port. We could just as easily have been talking about port F, right? But yeah, that's these are ports. Cool. GPI, yep. Cool. Excellent. Good. Oh, boy. All right. Are there any more questions? I did not quite succeed in my goal of getting through all of the slides today, did I? I'm probably going to skip these 2 slides. Maybe I would. Maybe I shouldn't. I kind of want to jump to keypad scanning. We did a great job with the slides today. Did we? Did we really? We got to like 28 and we started on what, 19? No, we started on 16. Okay. Well, that's not too bad. Can you tell this course is filled with Tron kids finally excited to be learning something Tron related? Yeah, no kidding, eh? It's like, give me the goods. You know, I'd like to take a moment and make like 1 or 2 observations about these slides in general. And I know that this is kind of the subject, and that like there's a lot of very technical stuff going on, but I kind of feel like, and I'm sure you guys will agree with this when I say this, I feel like this subject could use like a higher level analysis. Like, I feel like we get sucked down into the fine details of things without it ever being properly explained, like the gross details of things. So, like, the fine details don't make sense until you have the gross detail to, like, plug them into. So I feel like if I were going to redo the slides, I would focus a lot more heavily on the gross detail and perhaps back off of the fine details somewhat. Will you let us know in the next lecture whether it's 32 or 16 pins? Yeah, why don't we put that one on Piazza? Could you ask about the quiz? Yeah, ask me about the quiz. This content is interesting, but require too much brain power to understand. Yeah, really. Yeah. I'll do my best for you guys. Isn't program data stored in memory and instructions stored in instruction memory? Program data is stored in the data memory, not just memory. Memory is too general, too vague. It's like this SRAM region right here. And like, because of the way that the memory is mapped, these guys are actually different chips, right? The code will be stored in flash memory, but the data that like, you know, the stack and the heap and all of those regions, that's all stored in a separate chip, SRAM chip, because of course this is Harvard architecture, right? 16 pins per port. Thank you. Yeah. Yeah. So, like, while, yes, like, everything is stored in memory, like, you need to be more specific, I guess. This may be a dumb question, but what exactly are the GPIO pins used for? Like, if the SRAM has the data, what's the instruction memory? What's the GPIO's job? Oh, yeah, it's to drive LEDs, to read input from toggle switches, powering fans. You know all of the miscellaneous little electrical bits in your lab kits? The GPIO is how you communicate with them, right? No. Oh, yeah. Actually, that's a good question, Daniel. A lot of people got that question wrong, actually, for the program counter incremented question. A lot of people wrote like either 4 bytes or 4 bits. The program counter itself is incremented by 4, like the numerical value 4. Once you take that and map it to memory, it corresponds to 4 bytes, which is why I gave like part marks for people who said like 4 bytes. But like the technically correct answer is it's incremented by just 4, like the numerical value 4. So the GPIO communicates with the data and the instructions to other parts. Communicates the data and instructions to other parts of the electronic device. I would say the CPU communicates with the data and instruction memory in order to occasionally send a bit or two down into the output, and that drives LEDs, and that drives, that drives pins that connect to power transistors that drive motors and that kind of stuff. And the CPU will occasionally read from the input data register, right? This is your input data register right here. The input data register collects information from the circuit, like, is this push button being pushed? That kind of stuff, right? So, like, all of the any functionality that extends beyond the CPU itself and the program itself is handled by peripheral memory. Yeah. So the GPIO red counter is clock. Yes. Step number 1 to completing any test successfully: read the question twice. Read the question carefully. And it looks like a lot of people agree with me with the way that the slides are organized. Yeah. I got this question on the quiz, which I'm confused about. In CPU-based systems, only program data is stored in memory. Instructions are stored elsewhere. Yes. That's false. Instructions are also stored in memory. The alternative to being stored in memory would be like stored in punch cards or something, right? What do the ODR and IDR actually do? The ODR, output data register, when you set bits inside of this register, that the circuit picks up on them, sends that out to the output driver, and drives the pin with it. The input data register, if the pin is in input mode, it collects the information from the circuit, puts that information into IDR, and then, in order to use that information in your program, all you have to do is read that memory address by dereferencing a pointer to it. Yeah. I could ask for part marks, but I didn't get any. Oh. Well, shoot me an email. I'll take a look at it. Wouldn't it be true? No. Instructions are not stored elsewhere. They're stored in memory. So it's false. So when we did assembly, a register could only store 1 bit. But when we talked about registers, now they contain more than 1 bit. No, when we talked about assembly, a register held as many, registers have always held 4 bytes. Registers have even when we talked about assembly programming in 2MP3, yeah, if a register only held 1 bit, you wouldn't have been able to store numbers higher than 1 in it. The registers have always been 32 bits. I could... Oh, I have to do that meme now with the astronauts? Yeah. Here we go. Here we go. Let's see here. Memes. Where's always has been? There we go. No, I want to make a beam. There we go. There we go. Boink. Gonna save that to my memes. My memes thing. Save. Done. You can look forward to that being in the feed at some point. So, because they are stored in RAM main memory and the instructions are stored in ROM flash memory, they're both memory. Main memory and flash memory are both memory. So IDR and ODR are where actual read-write information are stored for GPIO. Bing, bing, bing! We have a winner! Yeah, that's where your read-write information is stored. Like, it's important to understand there's a layer between that and the actual pin. But, like, the whole point of memory mapped I/O is for you to be able to forget that there's that kind of electronics behind it, right? It's like it's an abstraction mechanism. So you can mostly forget the electronics behind the GPIO output port, input port functionality. You only have to be concerned about it when you're selecting a mode, right? Cool. All right. Thank you very much, everybody, for your time and attention today. Have fun. Have a good weekend. Bye-bye.